As you may remember, we have talked a little bit about trees and how they can be used. We mostly focused on the indexing aspects of trees. I mean, indexing applications of trees. So we either talk about how to make an index if there are a lot of search operations during the during access to a database or data source of some kind. So this data source can be like a map structure as well. So we can use these tree structures in order to facilitate access to the indexing of a map-based or an array-based structure. So when we are doing this is actually, if you remember, we talked about binary search trees. And even though binary search trees can be constructed in a balanced way, if we do not rely on any intuition and directly make the addition for an incoming number of elements to the collection of ours directly, we may end up with unbalanced structures. So let me give you a quick example. Not a solid example, but let me remind you what we have done. If you remember, we add some number of elements to a binary search tree one by one, and we end up with a tree, though a binary search tree, that looks very much like a linked list. But we add the same numbers again, one by one, not all together, but one by one, in a different order. So that way we can have a different tree structure with the same number of nodes, but much more balanced compared to the previous case. So, well, even though additions and removals are performant on the paper in these tree structures, according to some probabilistic ordering of events, we can get some tree structures which are far from the optimal performance of the tree that we have designed for. So in order to handle these situations, there are some heuristics, and using these heuristics, you can come up with different usages of trees in terms of indexing and in terms of other operations. So this morning, we are going to look at some of those variants which are balanced by nature, and we are going to examine the heuristics that makes them balanced. And afterwards, I am going to show you also another example. So the first four topics, other than the quad trees, the other four are mainly used for such indexing purposes, which I'm going to explain, and provide balanced tree by construction. And the quad trees are some examples of a special tree which is used for some different applications than indexing as well, which I'm going to explain to you as well. And there is also something called radix trees, which I will discuss when we meet again in the afternoon session. And it's being used for a completely different area. Well, not very much completely different, but it does have a different kind of usage. So this is mainly what our topic is today. Just give me 1 minute, please. The sun is showing up in going back. So I close my window blinds. All right, so let's begin. And one of the very basic structures that you can build in order to make a balanced tree is what's called AVL trees. And the AVL trees, these are the capital letters of the people who come up with this idea. And what you do in an AVL tree mainly is you annotate each node with a balancing factor. So the balancing factor is a number where it shows the maximum depth of a leaf when you consider that node. So if you look at this one, you see that there is a 1-2 hop way to the leaf. Now, for most of the almost all of our discussions today, we assume that there is also on top of the as a successor to the leaves, there are also some nodes which do not have any data. So you can assume like these are the null pointers inside this leaf. Okay, so when I say leaf, I actually refer to them. But in terms of from a practical point of view, these guys are actually the leaves. Okay, so please don't get confused when I say a leaf. So in order to take out this confusion, your book says these are your book calls these as the external nodes, but I will call them leaves nevertheless. So if you look, because all the height properties and such are counted by using them, so they are like the leaves of our tree. So if you look at this one has got a height of 2 if you consider this leaf. And if you consider these, it has got a height of 3 because you make 1, 2, 3 hops. If you consider this has got a height of 1, 2, 3, 4, so on and so forth. So you take the maximum number of among those, and it gives you the number, the balancing factor annotated to this node. So this one has the maximum depth 4. This one has the maximum depth 1, 2, 3. This one has, because that's the maximum depth. This one has 1, 2, so on and so forth. Okay, so why do you use them? Because then you will check whenever you make some modifications to the tree, then you check if the sibling nodes have balancing factors where the difference of these balancing factors are more than 1. Well, this actually translates if one of the subtrees is deeper than the other subtree by a difference of 2 or more. So that's why we call it an unbalanced tree. So if you look at this one, and if you look at all the siblings, the difference between those are 1. The difference between those are 1 because you see the depth difference between the left and right subtree is 1. And if you check all the siblings, it's all equal to or less than 1, which means this is pretty much a balanced tree. So if you find some couples which do have a difference in balancing factors, which is more than 2, more than or equal to 2, then you say this is unbalanced and you fix it. How you fix it is the catch. How you fix it by, for instance, let's have a look at this one. So what we have in here is assume that we are inserting this 54, so it's not there. Okay. So normally, when you look at this, what you would find is this guy has a factor of 3. Okay. So these guys has a factor of 1. This guy has a factor of 2, and this one has a factor of 1, and this has a factor of 4 because this is not there, and so on and so forth. So if you look at this, this seems like balanced because the maximum difference is 1. But when you add this, Let's take a look at this. So when we had 54, by the way, I forgot to mention the AVL trees. Is this structured like a binary search tree? So when you are making the additions, 54, you are going to go through, start from the root, and you say 54 is larger, so it should be on the right. It's smaller, it should be on the left. Larger should be on the right. Smaller should be on the left. So the address is clear. It's in here. So when you make this, there is an imbalance because now the balancing factors of this one is 5, 4, 3, 2, and this makes a difference of 2 between these two and these two. Okay, so these are imbalanced couples. And what you do is, actually, we have discussed this before, but we do something called rotation in this case. So how do we make these rotations is we either do it towards left and right, but they are the inverse of each other. So actually these arrows are two-way. So, well, there's no point in making this rotation because you make the tree imbalanced. So if you find, but you can assume, like, I should have a slide show. Yeah, you can assume that it is one of these two. So if you have this, you rotate it left and get this, because the imbalancing is towards the right-hand side. And if you get this, the imbalancing is towards the left-hand side, you balance it right and get this. And how you do this is, you see that there is an imbalance because, well, whatever you have in here, it needs to be balanced. So the difference between the depths in here is at most 1. And again, the same thing applies for this one and this one. But when you consider this one and one of those, and there is going to be 1, 2 difference, right? Because let's give numbers to understand. So that would be 3 and 2, or that might be 4 as well, but you got the point. The maximum is some number. Again, for this one, so the maximum depths might be, I don't know, 4 or 5. But then if we say this, the maximum depth of this, since this is +1, that should also be 4 or something like this. So you see, when I go to here, whatever I take, the maximum number from here, I would have add 2 to it. So this is imbalanced by nature. So what I do in that case is I take the middle one. Okay, so since this 2 hops is making the difference, I make the middle one. I assign it as a local root for these 3 guys. Okay, so this is like a local root. And this one is going to be on the left-hand side. This one is going to be on the right-hand side. And it's legal to do that because if I got 3 nodes like this, it means that A is smaller than B, it's smaller than C, right? Because all the elements in here are larger than A. Okay, so now you can put it like this because B is the middle element, and A can be the left child of B because it's smaller than B. C can be the right child of B because it's larger than B. So you can place them like this. But the question is, when you place them like this, what do you do with those subtrees, okay, of yours? So there are things which doesn't change, which is T0 on the left of A. This whole the elements in T0 is smaller than A, and A is smaller than B and C. So, well, the T0 is still with B on the left side of the left side of A. So even though T1 is the elements, T1 contains the elements smaller than B, it also contains the element larger than A. Because I know that because you go right and then go left. So these cannot be smaller because if I find a smaller element than A in here, it's on the right-hand side. So it shouldn't be on the right subtree. So this whole right subtree is larger than A. So I'm sure that the elements in T0 are smaller than A altogether. So I keep this connection. And the same discussion in terms of being larger or not is in here. So I keep this one in here as well. So these 2 are kept in the same place. What I change is since now B has two childs, A and C, I cannot keep it in here. I need to put it in some different place. And what is this place is, well, I cannot bind it to C because it already has some subtree, but the right side of A is present. So I can put it there because I already know that these are all larger than A, because I go once to the right, and even if I go towards the left, this T1 is still in the right subtree of A, and all the elements should be larger than A still. Okay. So what I do is I take this and I connect this to this. And T2, let's think about its place. Is it appropriate to keep it in here or not? So T2 is the elements which are larger than B, right? Because in the right subtree, but also at the same time, it's smaller than C because in the left-hand side. So you see T2 is here still on the left-hand side of C, and still on the right subtree of B. So I need not to do any modifications on T2 as well. So in other words, we can say something like this. So if you consider this, you have T0, all the elements are smaller than A, and then T1, all the elements are greater than A, but smaller than B, and then T2, all the elements are larger than B, and then C, because C is larger than T2, and then T3. You can write something like this from this tree. And if you look at this, you need to keep the same order to keep the binary search tree properties. And you look at this one, you go from T0, T0 is less than A, B, everything else, and then A comes, and then T1 comes, and then B comes, and then T2, and then C, and then T3. So this is also referred to as keeping the in-order structure. So in-order traversal would not be changed when you make the rotation, but the tree is more balanced. Because if you look at this one now, the difference between T0 and T1 is at most 1. The difference between T2 and T3 is at most 1. So since you add the same numbers to here, then the maximum numbers should be at most 1 different. Okay. But of course, this depends on the assumption that this was already balanced in terms of these, but not in terms of this and this. Okay. Because we accept that it happens gradually when you continue adding some new elements and new elements. So everything apart from these imbalance is already balanced, because the tree, your assumption is it's like induction. Your assumption is I already balanced my tree before this imbalancing has occurred. So everything else, all the other trees in my tree is already balanced. Right. So this is something called left rotation, and you can do the other way around, which I am not going to explain. Well, what you can do in an AVL tree is you can annotate the nodes not with the depths, but the difference between the left and right childs, left and right subtrees depths. So what you can annotate this one is with not 4, because it's not important. We are not going to compare it with something else. But what you would write here is 2 minus 3. It would be minus 1. And this one is 1 minus 1 is going to be minus 1. This one is going to be 0, because 1 minus 1. This one is going to be 2 minus 1, 1. This one is going to be 0. This one is going to be 1 minus 1, 0. And these two are going to be 0 as well. So you can make the annotation like this as well. If you do the annotation like this, it automatically gives you which way the tree is skewed towards, and what kind of rotation you might do. You can decide by looking at this. Okay, so if you get something like -2, this means it's skewed towards right, so you should apply left rotation, and otherwise you should apply right rotation. But this is not the only pattern to apply rotation. There is also this pattern to apply the rotation. Again, this these are two imbalanced patterns. Okay, if you look at this one, this imbalancing is between again A and B because of the two hops that you have. So even though these trees are balanced, there might be some imbalancing from within this depth and these depths. Okay, because let's say this is 4 and this is 3. So since there is a balance between those, this might be 4 or this might be 3. Both will work. Because if this is 5, then the difference between the levels is 5 minus 4, 1. If this is 3, then the difference is 4 minus 3, 1. Both works. But then if you look at this one, well, if the depth is 5 in here, and this means the depth for here, because the left and right, might be 5 plus 1 plus 1. So it might be as much as 7, which makes the tree quite imbalanced. Okay, so then we need to make the rotation. Now, in here, it's called a double rotation, actually. It's a double rotation towards left and right. And let's do the same consideration, how these is ordered. So it's like T0, again, is smaller than A. And at that time, the left subtree of C is all larger than A. So again, this all larger than B. So it's like T1, B, T2, C, and T3. It goes like this. Okay, so if you look at after the rotation, again, it keeps the T0, A, T1, B, T2, C, and T3 thing. So what you do in here is you see there is a 2-hop travel from A to B, and you want to make this travels 1 hop. The problem is it's towards one direction. So of course, in here, if you look at this tree, there is a 2-hop travel between A and C, but you go up and down, right? Then this keeps the balance. But in here, when you go 2 hops down, there might be a difference of 2 in depth between those, even if the rest of the tree is balanced. So what you do is, again, you keep the left child of A like this because it's on the leftmost side, and you keep the right child of C because it's on the rightmost side. This is also kept. And what you do is you put A as a left child of B. This is new. And you put C as a right child of B. This is also new. So now, since B has got new children, these two are orphans. So I need to connect them to new parents. So what I do is now, since everything in the left side of B is smaller than B, and there is A now, which is smaller than B, I go towards the A side, and naturally, T0 is smaller than T1, and T1 is larger than A, so I put the T1 in here. And a similar discussion exists for this. What I do is, this is all larger than B, so I need to go to the right. And as a C, T2 is smaller than C because it's on the left subtree. So what I can do is I can directly connect it to C. Okay, so you see, even if this seems like a very straightforward procedure on pen and paper, if you write the program, you need to be careful because you make a lot of connection updates. Okay, and it's very prone to errors. So this is, and there is, of course, the we have discussed the left rotation, but also there is the right rotation when you do the symmetrical case. So let's have a look at some examples. So this is one example. What we do in here is the case that we have just seen. So I have added 54 in this tree. So there's an imbalance in here, and the imbalance is actually caused by, well, you can also take that one. Okay, so that is also 2 hops. But what you do is you go as much as possible towards the root, and you make the update in here. So if you look at this, there is an imbalance in here. Okay, why don't you do it for here? Is well, well, you can do it in here as well. So that's an opportunity, but it requires it requires more operations. So you need to change the root as well. So you would try to avoid that as much as possible, because it's dangerous to play with the root. But you do it sometimes from time to time. But you can get the same result when you do the balancing in here. Okay. So you do it in here. So what you do, if you remember, when this was the case, what we do is this is the double rotation towards the right. So now 50 is the medium element. So I'm sorry, now the 62 is the medium element. So you put 62 as the new root. So let's check with our pattern in here. So you see what we do is that one looks like this situation in here. Okay, so what we do is this is the medium element. So I put it in the medium in the new structure. So I do it like this in here. So what I do, I put 62 in here as the new root among these two, and I connect this one to the left. I connect this one to the right, and you remember I keep this left child of this because these are the smallest elements among this structure. So it is kept, you see, and I keep this because these are the largest element in this structure, and it is kept. I do not do any modifications. What I do is, since this guy has new childs, I find new parents for this one and this one. So this one goes to the left of the right of this, and this one goes to the left of this. Okay, so if you look at this one now, if you look at the depths, so these siblings have the difference 1. These siblings have the difference 2. I'm sorry, 0, and everything else in order. So this subtree can take one additional element as well. So if there's an addition larger than 44 to here, you might do some additional rotations. Well, it depends on what you add also, but if there is an appropriate number coming in, you might do additional rotations to make this tree still balanced, because it's going to be placed somewhere like here, and that is going to be still balanced. But if this is the case and you add one more, so you see there's no way of rotating them and having a balanced tree still, because the number of elements in here has saturated. It's the most number of elements that you can keep in a tree of a height something. So since the height of this is 2, that one can be at most 3, and since the height of this one is at most 3, it can hold at most 2 to the 3 minus 1 elements, which is 7. So this one has 1, 2, 3, 4, 5, 6 elements. It can hold one more, but if you add 2 more, then you need to rotate it in the context of the whole tree. Then the root needs to be rotated as well, because it cannot carry anymore in the right subtree. Okay, so these are all the decisions that you need to consider when doing those. All right, so yeah, this is a removal. So if you remember, this was our tree, and let's say we remove this. Removing this one will make the tree directly unbalanced, because you see, then the depth of this one will be 1, and the difference between these two will be 2. and I need to make a rotation on the larger context, because I cannot make a rotation in here to make this deeper. Okay, I ran out of elements. Now this time, when the 32 is gone, oh, I'm sorry, when the 32 is gone, you see that there is this pattern with 2 hops, which I should rotate. Okay, so looking at this one, this is a single rotation towards the left because it's imbalanced towards the right. And what we were doing in here, if you remember, is we were assigning this one as the new root in here. And we were keeping this connection. This is kept. We were keeping this connection. This is kept. We were also keeping this connection in a single rotation, and this is kept. We were assigning this one to the right child of the old root. Okay. And if you look at this one now, it becomes balanced because this one has the tree depth 1, 2, 3. This one has the depth 1, 2. So the difference is 1. And if you look at those, this one has depth 1, this one has depth 2, which is okay. This one has depth 1, and this one has depth 1, 2. I'm sorry, this one has depth 0, and this one has depth 1. So the difference is 1, so no problem. And we get a balanced tree. Okay, so this is AVL tree. Okay, so, well, this is a good way of balancing a tree, but you see, I'm not going to go into the details of analyzing this algorithm, because you can have a look at your book, and it's been done there, and you are going to deal with those in your algorithm analysis courses a lot. But the problem with this one is, you see, there are some decisions that we need to do all the time by analyzing the overall structure of the tree. So we need to update all the depths. And if you do not update those depths, we need to recalculate for all addition. Practically, there are no differences. It is, even though it makes the searches always, it makes the tree balanced. So there is no possibility of doing some operation and coming up with a linked list like tree. But the way we make the balancing decisions and the balancing itself, well, making the balancing itself is not that complicated. It's not that costly, but updating the depth differences, it's quite costly. It's actually almost ON. Well, it's ON, but it's almost N, because you only don't do it for the leaves. So we can come up with better solutions, actually. And now there is something called splaying and splay trees. And what you do is you can do something like splaying at every operation that you do. Now, splaying, it is very like rotating, but the difference is you do not update some depths and look at the depths all the time, but instead you do it after every operation, if possible. So you might think that, well, what's the difference? But think about it. If these operations are not very costly, if they are constant time, and instead of updating all the values in the depth values in the tree at each operation, it is less costly to do this constant time operations after each addition, removal, and searching, even searching. In splay trees, what we do is we do the self-balancing by rotations again, but this time, in order to make the rotations, there are quite different patterns. They look like a lot, but they have some minor differences. So And it's about the how can I say that? It's about the strings series of nodes which we can find in a tree in different structural orders. So this is, in order to make this one easier to name and refer to, this is sometimes called as zigzagging. Okay, so we zigzagging is going to left and then right as a sequence. We do look at three different cases of zigzagging, so which is called zigzagging, and zigzagging. So you go left, 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 right, or right, right. So this is one possibility, which is starting from some nodes, independent of the left subtree, you go to right as a series of elements. So you see, these are perfectly okay to happen in a tree, and that might not cause an imbalanced structure, but also they have the potential to come up with an imbalance, because the T1 and these guys, you have structurally two depth difference. So what you do in a splay tree is you handle the situation quite differently. If you have a what you call a, I think this is called a zigzag. If you have this one, what you do is you keep this thread not towards the right hand side, but towards the left hand side. Okay, so the idea is, if that was imbalanced, then the only possibility that makes this imbalanced is to beat this one way too much shallow than these trees, right? Because if this is deeper than those, that is one case, and it might still be imbalanced this way, but a probable thing that makes this imbalanced is this is too shallow and these are too deep, and there are additional depth difference. So if you organize it like this, the deeper trees will be in here, and the shallower trees, this and this, are going to get automatically more depth by putting them as a child of this node originally in here. So this is called splaying. Actually, it's done by rotating, but you do rotate in a different manner. You make a double rotation instead of a single rotation in here. And another splay operation is a zigzagging. So you get a structure like this, a pattern like this. When you get a pattern like this, so you see this is the rotation itself. So you do a single rotation in here, and the idea is the same. And when you get something like this, so this is the same zigzag, but now you handle it in a different way, and you handle it like a rotation this time. Instead of taking this sequence and moving it towards this hand side, what you do is you take this one and you make this the new root, and so on and so forth. So it's just like the rotation. And this is also called, these three operations are called splaying operations. So the idea in a splay tree is you need to decide which, because you can handle the same situation in two or more different ways, you need to decide which one to apply. One idea is this. Another idea is, I'm going to be coming to that one in a few minutes. But here you can see some splaying operations, which are going to go good until some place. And one final operation is going to make the tree again balanced, imbalanced, while it might keep it balanced by applying a different operation. So let me show you this. So this is, you see, a zigzag. And what you were doing, how you handle this one is just like normal rotation. This one becomes the new root. And this is the left child. And you keep the left of left. And this is the right child. I'm sorry, this is the right child, and you keep the right of right. So there you go. And you make the, well, you find new parents for these two, but that will be this one and this one. So you see, it becomes more balanced if you do it like this. So if you look at this one, oh, I'm sorry. It is still imbalanced in some sense. So splaying doesn't make any difference in that case. So okay, well, maybe it might be if you think about the additions. Now, if I add some numbers in here, that would they can go towards this side. So this side is kind of full in terms of greater than 13 additions. So you see, if I want to add like something like 15 or so, it is always going to go towards this side. But if you look at this one, well, it's quite the same. It doesn't matter a lot. So you see, this splaying, well, it didn't make any kind of a difference at all. So that is the situation in splay tree. So you might apply the splaying operation. It doesn't remedy always your situation, because you see, you don't holistically, as a whole, you don't look at the depth differences and fix the depth differences. Okay, it's like what for any kind of operation you do, which I'm going to come to in a few minutes. So at any kind of operation you do, you might do the splaying in order to change the structure of the tree. But on the other hand, that might have a different advantage. Okay, it doesn't do anything in terms of fixing the imbalancing, but it might have a different advantage, which I'm going to talk about in a few minutes. So let me continue. Now in here, our tree looks like this. And what we can find in here is this structure. So there are a lot of different, so you can find a similar structure in here as well. And you might apply splaying in here as well. But important thing is you do the splaying as you do some operations. After each operation, you do the splaying. So we will talk about this. And please do not forget this situation. I'm going to come back to this. So why do we apply splaying in here instead of in here is about the operation you make. And when you make an operation, according to where you do the operation, where the operation affects, you do the splaying in here. Okay, so if we are doing the splaying in here, it means that we are adding or inserting or removing or searching something at this portion of the tree. So that's why we are doing the splaying operation in here. Otherwise, we would have to look around the whole tree and make series of splayings, which is the same as the ABL tree logic, right? Because in there, we were also going inside the tree, doing a lot of depth calculations and making the necessary rotations. And that one is more is a costly thing. So in splay trees, instead of doing it over the whole tree, you apply the splaying after each operation, and you do the splaying at the point where the operation affects the tree. Okay. So let's have a look at this one. So if let's assume that we are doing something over this portion, and we find out this series. And well, there are a couple of ways which you can handle it. You can handle it like putting 12 and putting 11. Oh, sorry, 11 at the left-hand side, 14 as the right-hand child, and restructuring. Or you can do it like 14, 12, 11, restructuring. Okay. So what we do is the second one. So you see, it is the pattern that we have checked the first. 14 now becomes the new parent of 11 and 12. So we get this series and we skip it other way. And we splay this series. So it becomes like 12 is the left-hand child, 11 and 13 are the childs of that. And you see, this one has made a lot of progress in terms of balancing the tree. Okay, so when you do something over here and you do the splaying, now it has become more balanced. So let's do one more. Okay, now again, we do some operation over right-hand side, and we see a zigzag in here. So what we do is we take this one and we apply the fixing operation. Now again, we can do 14 in here, 10 and 8. We can fix these three like this, or we can fix these like 10 in the middle, 8 and 14 in two different ways. Okay, let's see what we do. We did the first one, even though I believe the second one might be better. We did the first one in here, and we changed the structure like this. But I think it would have been better if we do the other way around. So it might be like, if we have got the case, we do the 10 as the new root, 8 would be on the left-hand side, and we put this on here in 8, and the right-hand side do remain, and we put 14 in here, and the left and right child of the 14 do remain. So you see, this way it's a more balanced tree. If you do it like this, it's not as balanced as this situation. But this brings us to the point to talk about the operations that we make displaying. So it's easy to understand when you do displaying in insertions and removals. Okay, because when you are inserting and removing, there is the possibility that you change the structure of the tree. And what you do is when you insert, you display the new node. So you look for displaying opportunities in the new node. Okay, so you just do not run around in the tree looking for displaying opportunities. Whenever you make the insertion, you look at the inserted node and look for displaying patterns and apply if there's a possible displaying operation. And for the removals, you do displaying over the parent of the deleted node. So you look for the operations, which means in here, we might choose to display like that because of these two rules. It might be like, well, one of these is being inserted and removed, inserted or removed. That's why we choose this. Or one of these might be being searched. So since the rebalancing is an ongoing operation always in display trees, so it's not like you take the tree as a whole and you rebalance all of them at once. You do the rebalancing during the searching as well. So it is good because of two reasons. Because displaying, one of them is you keep the rebalancing in the searches as well. So whenever I search for something, I rebalance the portion which I'm searching for. Okay, and the rule is if it's like a binary search tree again, the display trees. If we find the node which we are searching for, we display that node. So look for displaying opportunities, displaying patterns. And if we cannot, we will be ending up in a leaf. So we display the leaf, okay, towards the root or whatever kind of opportunity is there. So this is good because, as we've discussed, we are continuously making a balancing operation inside the tree by this way. And this is also good because when we search and rebalance, now let's have a look at the balancing operations in here. Okay, suppose that we were searching for 30, okay, and we find something like this. We bring the 30 towards the upside. And let's have a look at those. Suppose we are searching for 20. Now, when we do the rebalancing, 20 goes up like this. And this is another one. Again, in this one, if we were searching for 20 and we do the rebalancing, 20 again goes up. So this is doing something. It is, whenever we search for something, it is bringing the searched node towards the up-hand side, right? And if we do keep searching the same number over and over again, it will go towards up over and over until the root, which means replicated searches over the same thing or over this near nodes, okay, brings those nodes towards the up, which means better search times in the next searches. So if something is being continually over and over searched, you cannot, you may think of this one as not as a sequence of searching, but you search it very frequently. As frequent you make the searches, this node starts going up, so you find it sooner. Okay, so as if you make a lot of searches over some group of nodes, they keep going up. And even though this tree becomes imbalanced, the frequently searches, since they bring up the nodes that you are searching for, the frequent searches becomes more and more performant. Okay, and this is the good thing. This is the thing about the splay trees. Okay, I hope it's been illustrative. I was able to express the main logic. Okay, this makes the dynamic balancing, the display tree makes the dynamic balancing this way. So let's take some number of examples in terms of insertion. So what we do in here is we continuously insert some numbers. So we newly insert the 2, and we do apply the splaying in here so that 2 becomes the root. So it seems like it doesn't make any sense to do this because it's the same structure, you see. But what is the different thing is 2 is on the top instead of 1. But why do we do that? It's very probable in practice that we want to access the newly sorted thing. Think about a stack, right? So because of these patterns, because of these possibilities, these structures make a difference. So just like it, when we put the tree, we try to splay it towards the top as much as possible because it's probable that we are going to. So if you look at this, the oldest node is 1, right? So this is the oldest one in our collection. And now when we add the tree, it is in the deepest place. So this has some meaning because since this is the oldest, in practice, it is not very probable to access this one in a sooner time. It might not be the case. You might have a different kind of access pattern, but then you don't use the splay trees. So the splay trees tries to bring the newly accessed data towards the upper levels of the tree as much as possible. So you put the 4 and you make it like this. So you see this is pretty imbalanced, but the newly inserted element is on top. Again, let's have a look at the removals. Okay, so suppose that we have a tree like this, and there's 7 in here and 8 in here. And what we do is we remove the 7. I'm sorry, we remove the 8. And when we remove the 8, we carry the 7 as the root. So this is one way to make the removal. We have done it in a different way in binary search trees. But one way to do it is take the rightmost, the biggest element on the smaller side and make it the new root. Because it makes most sense, right? Because something you are taking out of a tree, and the next thing to be the root to make it balanced will be the smallest one on the right or largest one on the left. So you take the largest one on the left and you make it the new root. And then you look at the parent. I'm sorry, if this is the root, you look at one of the childs. So you look at the child on the left and you look for some splays like this. And when you find the splay, you apply the splaying operation. You find the pattern, you apply the splaying operation, and you do it like this. So you see the 6, which is very close to 7, which is in the root now, and it is very close to 8, is on the upper portion of the tree now. Okay. And if you are searching for 6 now, let's assume that you made a search to 6. You make another splay operation over the 6. So you take this splay and you try to take the 6 towards the top to make the pattern like this. All right. Okay, so this is the logic behind the display trees. Well, if you are keeping only a single element in a node, this is more or less as much as you can do. Of course, there is also the red-black trees, which we are going to talk about in a second, but it's related with what we are going to discuss now. And the thing that we are going to discuss now is the multi-way search trees, or sometimes called, well, there is a specific type of multi-way search tree, which is 2-4 trees. Okay, but what this tells us, multi-way search tree, is we can keep more than a single element in a node. But if we keep more than a single element in a node, then we can have more than one descendants, because if you want to keep the binary search tree property, then if you have a single value, you have the bigger ones on the left, you have the larger ones on the right. But if you have two values, you can imagine that the smaller ones than the smallest element in your node will be on the leftmost side, and the larger one than the largest element will be on the rightmost side. But what about the things in between? Okay, so if there are more than one element, there are many inner elements as well. So there are many ranges as well. So you do it by following some, again, principles. So if you look at this tree and look at the nodes 22, so you will see that it's like a binary search tree, because if you take all the numbers in here, they are smaller than 22. If you take all the numbers in here, they are larger than 22. But if you look at this node, for example, there are two elements, 5 and 10. The left node, all the numbers in the left node is smaller than 5. All the numbers in the right subtree is larger than 10. But there can be numbers between 5 and 10. And what you do is you keep an additional link. You keep an additional child for this one, and you would put these two nodes in here. And you can have as many different numbers in here as well, as much as possible. But according to different numberings, they take different names. One frequently used one is 2-4 trees. So there's 2-4 trees. In this 2-4 trees, what you do is you limit yourself, with 4 descendants. Okay, so whenever you got a node, there might be at most 3 numbers in that node, and there might be at least one number, because having a node without a number, it doesn't mean anything. So you are going to have at least 2 childs. So that's why it's called 2-4 trees. You at least have 2 descendants, at most have 4 descendants. So it's the number of descendants is between 2 and 4. So, well, that is not something very different from what I have just explained to you. But you can have nodes such as this one that might have more than 2 elements. And in that way, this means this node is going to contain numbers which are smaller than 6. But of course, it might not be possible due to the structure of this. But if you are holding doubles, it should be that 5.5 should be in here. And in this node, there should be elements between 6 and 7. In here, there should be elements between 7 and 8. And in here, there should be elements which are larger than 8. So this is the idea. And well, of course, things are not that simple when you do it, because from time to time, when you make the additions, some nodes can overflow or underflow, which means when you're trying to make the addition, you might come up with more than 3 elements in a node. Or when you remove something, for instance, let's assume that we are removing 11 in here. Well, then this node becomes empty. So what I'm going to do? Okay, so I can leave it as it is, but I can make a restructuring as well, so that now removing this one does make this tree less balanced, right? Because In here, it's like a complete tree, but in here, there is one missing. So you might do some operations according to, for the worst, if you are taking 15, then again, things are pretty much more complicated. What you're going to do, you take 14 up. That is one way to do. But what if taking this one up makes this empty? Okay, so there are issues like this, and you deal with those issues when you are dealing with 2-4 trees. And most of the time, the operation, the insertion logic is simple. You try to insert the number to the root as much as possible until you overflow. So for instance, in here, because even though having a logarithmic depth is good, you still want your tree to be not very deep, right? Balancing is about this. You don't want to make your tree deeper. So what you do when you are adding towards the root, so as much as possible, but at one point, it's going to be more than 3 elements, so you need to split your node. When you are making the splitting operation, it doesn't make sense to keep this one in the root or keep this one in the root, right? Because if these are in the root, then the right-hand side will be all going towards the right or vice versa. So what you want to do is you want to take the middle elements, one of those, either this one or this one, and you make that as the new root. So you split it to 2, you take 12 to the root. So this is the left-hand side because it's all smaller. This is the right-hand side because it's all larger. And then the tree becomes like this. And then now it might not be possible to continue adding the root. So if I told you that you add the root as much as possible, you can do it if you add 13, right? So you can put the 13 in here. But you cannot do it for example, 3, because if you put the 3 in here, there are larger elements in here. So it doesn't conform the binary search tree property. So what you do is, again, you do the same thing, but you put the new number to an appropriate node. So if you got 3 to be added, you go to the left, you add it to this node. And you make it to overflow as much as possible. You wait for it to overflow. Now, things can get nasty when you have the overflow at the deeper node. So if you want to add 5 as well, it will go to the same node, but it will make this node overflow. So now you might split this node just like we have done in the past. So you might do it like, okay, now this one has overflown. So I'm taking this node out and I am putting 5 and I'm putting 3, 4 in here and I'm putting 6 in here. But what you have now is a deeper tree than it should be, than it might have been. So what you do is you, instead of splitting, you should decide if I want to split or if I want to move some value towards the root. And then again, there are a few opportunities in here. And what you can do is you can take the 6 and move to here, and you will be happy. Okay, so then this one would be 6, 12, and the right-hand side would be 15, which is okay. And the left-hand side would be all small numbers, which is okay. But there is this one as well. Okay, so if you do it like this, there is an opportunity that this one is going to be overflown again. Because if you want to add 2, then this one will overflow again. So what you can do is you want to keep the nodes as small as possible. Instead of moving the 6 towards the root, you can move the 5 towards the root, like this. And then, of course, you need to split your root because 5 is going up. Then you have the larger nodes and the smaller nodes. But since 5 has gone here, the things between 5 and 12 should go here. So 6, the splitted 6 would be a new node in here. And then when you add something new, like 10, it's going to be more balanced because it's going to come to here. And then you add something like 8, it's between this and this. So you keep the ranges as much as possible in the inner nodes. Because if you do this, then you would not have to overflow and split down towards the deeper size of the tree. and grow the tree towards the lower side. Okay, so this is the main decision that you do during the insertions. And when you are making the removals, it's more painful, because then you need to sometimes, instead of split, you need to join. Okay, let me show you. So suppose that you have this tree and you are removing 4. Now you have an empty leaf in here. And what you can do is you just can leave it as it is. Okay, but then again, what if something new comes in, like smaller than 5 and 10? So you need to rebuild that node. And you know, the memory allocation is not cheap, it's costly. So once you build some node, it's good to keep it there as much as possible. So what you do is, when you take this out, you push one of these elements in here towards the downside, but then you have a single element in here which violates this, because then it needs to have 2 childs, but it has 3 childs. So what you can do is, if there is some node with 2 childs, you can take one of the nodes up, one of the values up. So you see, this one causes 5 to go down, 6 to go up, and it causes a tree like this, which is again quite balanced. The root is in here. I'm sorry, this node is in here still, and it has got 3 descendants, like smaller than 6, larger than 10 in between. But it requires a lot of checks. So what you do again is, you might, just like a heap, when you remove something, instead of doing all the left-right restructuring, you can take the largest value in the right-hand side and you can move it to the root. Okay, so you do not need to work a lot on restructuring now. And you put 11 in the root. Now this is empty. And since this is empty, you can carry something down below. Now, again, when you carry the 10 in here, this need not to have 3 childs. This need to have 2 childs. So you need to do something about it. So you might not carry this 10 towards the lower side at all. But if you do it, one way to do that is, you might join the 8 and 10. So that now it has got left and right elements. Okay. So as we discussed, you might not do that at all and keep it that way. So just this one is not present anymore. You can delete this, and you can have 6, 10, a smaller node in here, medium node in here, and there is no bigger nodes. But then, of course, it depends. But then you limit yourself in filling this part of the tree. Well, it depends on what kind of insertion removal patterns you may have. So it's a decision which doesn't have a single correct answer. And then again, I want to remove 13. So I can do it right away, because the structure is supporting that. And then from the structure, you might want to remove 14, which makes this empty. And this one is, well, not very nice to have. So you might do a couple of restructurings. You might push 15 towards down. And now this is empty. And since this is empty, you would want to join that one with that one. But then again, joining that with that is going to make these 2 nodes to be joined. So it would be like, if you do it right away, then it would produce you a tree like 11. Oh, 11, 6, and blah, blah, blah. Okay, 15, 17, 8, 10, and 5. So this is not, so you see, this has got 3 childs while it should have 2. So what you do is, you also push this one towards the downside. So you remove the root, and the new root is the joint version of this. So it has got 2 childs, 3 childs. And also, yeah, these 2 nodes are joined in here, and you get this. Okay, so you see, it's a lot of different possibilities you need to consider. But there are some rules that you might use in order to facilitate these moves, these joins. And one of these is something called a load factor. So it's like at most how many numbers can be in your node and how many do you have? So you try to make each node follow this node factor as much as possible. And when you do this, you have something which is called a B tree. Okay, so if you do it like in a heuristic way, like what we have done right now, it's a multi-way search tree. When you define a rule for this, so that you say that, okay, my tree is going to have, it doesn't have to be a 2-4 tree. For example, if you look at this one, it might hold up to at most 5 numbers in here, but you define some rule that, well, at least 20% of my nodes should be full. So I'm going to do the restructuring, rebalancing according to this load factor rule. So you check for your nodes, and if one of your nodes has a single element, then you need to restructure the tree so that that one will not have a single element anymore. None of the nodes would have a single element anymore. Okay, so in practice, this works quite good. And these B trees are used a lot in practice for most of the systems. So there is something called B plus trees as well. And this B plus trees requires you spare one of the nodes so that you can keep a linked list. Let me do it in a different color. You can keep a linked list of leaves. Okay, so you spare one of these in order to use a pointer towards the next leaf. So it's easier to traverse the leaves this way if you do that. Yeah, but it's now in the context of this lecture, if you take a advanced database lecture, maybe you are going to deal with those a lot, but it's good to know about these under the context of this lecture. And it's good to understand the basic idea behind it. So this is the basic idea that I have been that we have been discussing. So we will continue with red-black trees, but I would like to take any questions if you have. All right. So now the red-black trees are actually a different representation of a 2-4 tree. So what you do is instead of holding multiple elements in a tree, you mark your nodes with either red or black. Okay. So whenever you have red and black nodes coming one after another, it means that you are going to join those nodes. Okay. So actually, if there are if there is one red and one black colored node, it means that they are actually joined, but you do not want to keep multiple elements in a node, so you write it in a different way. Okay, so if you think about this one, this is like having this 5 and 10 together, and then less than 5 goes here. The 7 goes in the medium node, and the 11 goes in the right node of the joint nodes. All right, and these also can be joined, and so that you know that the medium node of 5, 10 is actually again a triple node. Okay. So, but here you don't do multiple elements in a node. Here you have red nodes and black nodes. So there are some rules when you are building your tree, when you are making an addition, insertion, and removal, and you want to keep your tree following these rules every time you make an addition and removal. The good thing is, if you come up with some patterns when you are adding or removing, you look at these patterns, fix them, and automatically make your tree follow these rules. Okay, so this is the idea. So it's like you do not check the whole tree every time you make a modification if it follows the certain rules, but you just check the local places where you make the insertions and removals, And according to some patterns, if you fix those, then the tree would automatically be conformant with your initial rules. And if it's conformant with your initial rules, then it means that it is balanced. And the rules are here. The root is black always, and the leaves are black. So these are the leaves, okay? So the external nodes, so they are null nodes actually. So the leaves are black always. And in the inner nodes, there are two rules when you are making a node red. Children of a red node should be black. So no two red nodes should be parent of each other or children of each other. So it's always the blacks are the black nodes are the child of the red nodes. So if you look at this tree, whenever you look at the red nodes in here and those guys and this guy, you see the children are black. Okay, and the next rule is what makes the tree balanced. All leaves have the same black depth. And what is the black depth is when you start from the leaf, go towards the root and count the number of black nodes, it always should be the same, right? So this is quite balancing. So if you look at this one, 1, 2, 3 black nodes. Since the root is always black, I do not need to count the root. Since the leaf is always black, I do not need to count the leaf. So it's 1, 2 black nodes. If you look at this, 1, 2, 1, 2, 1, 2. If you go up, 1, 2, go up, 1, 2. And you go up from here, 1, 2. You go up from here, 1, 2. You go up from here, 1, 2. And you go up from here, 1, 2. See? So the cool part about this one is when you assign a color, it might change, okay, according to the pattern that you see. Now, how is this? Well, under what circumstances I might need to change the colors or restructure? Imagine we add 9. Okay, so this is still a binary search tree, by the way. So if you are adding a 9 to here, so it will go to the left, to the right, to the left, to the right, to the right, and it will be added to here. So 9 will come to here. Now, if you look at this, there are two possibilities. Either I add this one as a red node, which is not possible. So there's only one possibility in here. If I add this one as a red node, then the red's child will be red, which is not allowed. So this should be a black node. But then if I add it as a black node, let's count how many black nodes do I have starting from here. So if I start from here, I would have 1, 2, 3 black nodes, which violates the last property. So what I can do is, well, is it not possible to make this red and change this to black? So let's say this is no longer red, but it's black. And then what's going to happen? Again, let's count. If I start from here, there is going to be 1, 2, 3 black nodes. So you see, this 9 addition is quite imbalancing. So you need to restructure your tree somehow. So let's have a look at it. Let's see how that is being done. So there are now some patterns that you need to handle. One of the patterns is 2 red nodes. So think about this. Think about the previous situation. If I add directly a black node, that would directly violate the number of black nodes until the root property. So I should add it as a red node, but then there would be 2 red nodes in child of each other. Now this one says if you have got a situation like this, what you need to do is you just take one of the parent red node, make it a black parent, take the parent of the red and the child of the red and make them the child red nodes. Okay, so let's see if that works in here. So the case was if I add the 9 as a red node, then that would be a problem because of the 2 red nodes. Then what was the remedy? The remedy was make the 8 a black parent and make the 7 the child of the 8. So let me rewrite this part. Okay, so 10 stays. So I'm rewriting the left. Let me do it like this. Okay, so let me write it in here. 9 and childs. And let me erase it. Like this. So what I'm going to do is, if you remember, 8 was the red parent of 9. So I'm going to write it as a black parent in here. Oh, sorry. I'm going to write the 8 as a black parent in here. Okay. And what was there? There was 7. And 7 would be a red child. And 9 would be a red child. And both childs would be black at that time. And there was also 6, a child of 7, and it was black. Okay, and my tree would look like this. Oh, I'm sorry. So let's count if that obeys the rules. So we see that now these guys have 1, 2 nodes until the root, but this didn't solve my situation because this 6 is in here and it has got, if you count from here, 1, 2, 3 nodes. So that might still not solve my problem. So we might have to look for other restructuring opportunities following some pattern. This is just one pattern. Okay, there are additional new patterns that we might take a look. So the original was like this. Okay. Oh, 6 was, by the way, 6 was a red node. So it still, yeah, if you look, 6 was a red node. I'm sorry. So it still has got the problem of having 2 reds. Okay, child of each other. So you see, it still didn't solve my problem. So what is going to be the solution is, now we will see that there are some patterns when you need to make this one red as well, and then there are 2 reds, and then you need to restructure this tree. Okay. So let's have a look at this one. This is another pattern. If I got some situation like this, when there's a black node and there are 2 red nodes coming one after another, just like this situation. So it is like 9 in here. Let's see how we are going to solve this issue. What we do is we change the colors. So we make the root. So we didn't, oh, I'm sorry. We didn't change any, we didn't make any restructuring, but we changed the colors. So let's see how is that going to happen. So if I add 9 as red in here, I make this black and I make this red. But if I do this, now you see there are a couple of red nodes coming one after another. So what I need to do is going to chain reaction, some changes. So what I need to do is follow the other pattern. So now the 10 is going to be placed in here. 5, 3, 4 is going to be placed in the other side, and then so on and so forth. Okay, and it might still not solve the problem because there might still be some, I might still do some restructuring over the whole tree. Okay. So this will cause a chain reaction of new additions. Okay, so let's see some more basic examples. So what we do is we continue to add some new nodes. So this 7, oh, sorry, I forgot to. Sorry, I have got a mistake in here. This should be red. Your book uses blue instead of, it calls it red, but it uses blue nodes, which is, I don't know, it was very hard for me to see what's red and what's black. So I put a red circle around the red nodes. Okay, so let's have a look at this one. So if you look at this one now, I add a new node as red. So you see there are no black nodes in the way. I can continue. I add a new red node. And since I've got two red nodes coming one after another, I restructure it like this. And then I add a new number, 15. It's going to be added as a red node. And then again, two red nodes. Because if I add it as a black node, then that would that might keep the balance. But if I add it towards a new level, then it will automatically change the balance. Then I need to add it as a red node. Then I look at this one. So there are the situation is like this. What I do is I change those to black. Okay, and this is a pattern you can do. And then I add 3 as a red node. Nothing is bad. I add another node. Everything is all right. There are still, if you count those, there is a single black node towards the root. And when I add a new node, like 14, there are again 2 red nodes. And then I make the restructuring. And you see, it directly makes the tree more balanced tree. So I add another one. So then there is this pattern again where I make the change and make this one become red. These become black. I continue adding. Now this is another addition. So this is a binary search tree, by the way, as the values that it's keeping. So there are 2 reds, one coming after another. So I make in here another restructuring like this. So these all follow this pattern. Okay, so you see that this guy where I got 2 reds and I got a sibling red as well. So if I see this, I change it to this. I continue to keep adding, but now you will see that there is going to be some chain reaction in here. I add this one, 2 reds coming along. I change the colors. And when I change the colors, again, I find another 2 reds coming one after another. And here I make the rebalancing and I make this root now. This one makes is becoming the child with the color red. So it becomes something like this. So you see, it's actually a rotation. We rotated towards the left. And let's take a look at some removals. Now let's imagine we remove 10. Okay, from our original tree. Let's say that we are removing this one. So what we will do is, well, if we follow our original removal idea, it will be 7 would be the child node of 5. And 11 would be the child node of this. But if you do this, then there is going to be 1, 2, 3 steps towards the root, 3 black nodes towards the root, which for here, 2 black nodes. So when we make the removal, again, we look for different patterns, some patterns. So these are the patterns that we are looking for. So the bold lines represent the removing node. So 40 is going to be removed. And the blue node is either red or black. It doesn't matter. Okay. So this one can be red or black. It might be either one of those. But if you got to remove this node in the right-hand side, so now you can be sure that there is going to be an imbalance in terms of the number of black nodes towards the root, because for all the elements in here, one of the inner black nodes are going out. So the number of black nodes until the root is actually being reduced by 1, which causes the imbalance. So what you do is you turn either this one or this one to this, which means the farthest child, red child, becomes now black. Okay, I'm sorry. Well, if it is the left child, then it becomes black. If it's the right child, It becomes the root. The color is not important. And then you keep the rest of the structure as intact. So the 40 is still the right child of 30 in here. But what you do afterwards is you remove 40. So you do whatever you are going to do with the left and right childs of 40, because these ones are going to change. So you see what we do in here is, if you take a look, since we know that the number of black nodes towards the root will be reduced by 1 if you go from here, what we do is we also reduce the number of black nodes on the left-hand side. Well, actually, to be honest, we do not reduce it, but we increase the number of black nodes on the right-hand side by 1. Okay, so you see, what's different in this pattern from these patterns is, in here, there is a single black node in the left-hand side and a single black node in the right-hand side. In here, there is a single black node in the left-hand side, 2 black nodes on the right-hand side. So this is perfectly okay, because this one is going to go out. So this is one pattern. This is another pattern, and it has the same idea. So you see, again, when I remove 40, there's going to be 1 less black nodes in here. So what I do is I change the colors. So now there are, if you go from one of the subtrees of Y, there is still going to be the single black node, because it was 20 in the previous state, it's 30 in the current state. But now there are 2 nodes, 2 black nodes if you go from the right-hand side. And when you remove 40, then it's going to be equal again. And this is another pattern. So when you have all black nodes and you are going to remove 40, then you do make this one as red. Okay, and then you remove 40. Again, the same logic in here. You decrease the number of black nodes. Actually, it's a little bit of a different logic. Now you don't add a black node on the right-hand side, but you decrease the number of black nodes in the left-hand side paths. And here's another pattern. So here, again, you are going to remove 40. What you do is, if there's a single red node in here, you rotate these 3. Okay, so you rotate these 3 nodes in here, so that now, let's check. If you consider this, all the way up to the root is the same number of blacks, and all the way down to the left and right-hand side, the same number of blacks, but one of them is going to go away. So I need to make them 1 different. So if you look at this one, again, considering here, when you go up, the same number of black nodes. When you go down, on the other hand, if you come from here or here, now there is going to be, in this situation, there was only a single red node in here, black node in here, and there was a single black node in here, right? Now there is the single black node still in here, but if you count this now, there's an additional black node in here. Okay. So let's see some examples. Let's have a look at this one. Now this one has many nodes, and what I remove from here is 3. So when I remove the 3, there's no problem, because I'm removing a red node. If I remove something else, for instance, like 12, then 1 black node is going away, which means I need to restructure this point. And how I do restructure it is I rotate it once and make the 7 a black node. Okay. So I might not just add this towards here as a black, because it violates the binary search tree property. Now let's have a look at this one. Oh, sorry. So you remove different from the others, like 17. You remove this one, and it can go away because it's red. And then you remove 18 in here, then one of the red black nodes has gone away. What you do is, by following the patterns, you switch the nodes, the colors of these two. And then now you have 1, 2, 1, 2, 1, 2. And then you remove 15, which is okay, because it's a red node. And then you remove 5, and 4, sorry. Then you remove 16, which is a black node, which means restructuring. And what you do in here is, well, you make the rotation. So 5 becomes the root now, and the colors are exchanged. So now if you check this, there is 1, 2 black nodes, 1, 2 black nodes. From here, 1, 2 black nodes. From here, though, we have 1, which means it's still not balanced. So we check for another pattern. So we check for this pattern. There's a pattern like this. And when you have a pattern like this, you switch the colors. So this is red, this is black. So now it is 1, 2 black, 2 black, 1, 2, 1, 2, and 1, 2. Okay. Well, you do not need to memorize all of this because it's a lot. But what you need to get from these discussions is, well, there's a for the rebalancing structures, you look for patterns to make the rotations. And according to these patterns and rotations, you do the rebalancing as you make some additions and removes. Okay, in an AVL tree, in order to do this, you need to traverse the tree as a whole all the time, which is costly. And as we have further progressed to new and new structures, you have seen now new approaches to make the self-balancing on the tree. Now, there's also one more thing, which is called the quad tree. I'm going to talk about it, but let me leave this to the afternoon session because I actually have covered most of the things that I wanted to cover. These are pretty much all kind of different trees that you might see. Actually, red-black trees are what's inside the map structures and the set structures in C++. So if you debug and jump inside the map structure functions and see the source code, you will see something like RB tree, RB node inside when you are debugging. These are the red-black tree nodes. So red-black trees are the structures which are used by C++ in the self-balancing structures, self-balancing collections as trees. You might check that out. Okay, it's very good to know these kind of things. And yeah, this is pretty much everything that I want to discuss in the morning. Do you have any questions? Of course, it's hard to grab all the details at the first time you learn about those. But it's also important to know what you are trying to, what you will deal with whenever you want to implement something, or what kind of a structure you want to use when you have a situation. So that would be a good introduction, I believe, to you for about the self-balancing trees. If you want some more information, you can always read your book. There are some codes in here as well. You can check those out. But like I told you, for your level just now, you are not required to go further deep down. And you will do in the upcoming years. If you want to act early and learn about these things in more detail, you can do over your book. Yeah, that is pretty much all.